Hola amigos, so now let's continue to our next topic, that is absolute and service ceiling and time to climb, at page number 432 and 435 of chapter 6 of Elements of Airplane Performance. And the book we are following is Introduction to Flight 6th edition by J.D. Anderson, special Indian edition. And in absolute and service ceiling, as you know, the ceiling of a room is the top surface of the room is the ceiling, and from aircraft point of view, the ceiling is the height, the maximum height an aircraft can attain, or the maximum height at which an aircraft can fly a steady and level flight. Okay, so from these graphs we will determine the absolute and service ceiling of the aircraft. The absolute ceiling is when the aircraft is flying at an altitude above which it cannot go. Okay, so it is the maximum altitude it can attain. Okay, so at that point maximum rate of climb will be 0. Okay, because at that point it cannot go any higher above that point. Okay, so at that point, if we say this is the power required curve and this is the power available, maximum power available curve for a propeller engine, we know power available is this, quite constant, and maximum power available is this we are talking about here. And therefore this difference between maximum power available and power required at a height which aircraft is flying is the maximum excess power with which an aircraft can climb. Okay, the maximum excess power is there to make an aircraft go from an altitude to another altitude. Okay, so if we say that the aircraft is climbing, okay, it has got some maximum power to move up to a certain height, then if it attains that maximum excess power which is available to climb at a certain height, then we see that at that height power required, we know power required graph was here, it moves upward as the aircraft moves upward, also the power required moves towards right and also rotates clockwise. So it keep moving upward, power required curve keep moving upward, okay, towards right, and also rotated a little clockwise over here. And power available here, actually maximum power available to the aircraft, we know the power available was here, and as the airplane moves up, the power available curve moves down. Okay, so here we see maximum power available, which is here, has moved down, and power required curve has moved up. So the maximum excess power with which an aircraft could fly or could attain a height has come to 0, or say the difference between the maximum power available and the power required is 0 when these curves meet at a tangent point. Okay, so if we see from this graph that maximum rate of climb is on x-axis and it varies with altitude, like it is decreasing as the height is increasing. Okay, the maximum rate of climb at which it can go from this height to another height will decrease. Okay, so here at sea level, that is at height equals to 0, the rate of climb is maximum. So as the aircraft goes up, the maximum rate of climb decreases, and it goes, as the aircraft goes up, it attains a maximum rate of climb of 100 feet per minute, which is 30.48 meter per minute. It is actually meter per minute. Okay, and this point at which the maximum rate of climb is 30.48 meter per minute, this altitude is the service ceiling of the aircraft. And as I said above, that the maximum altitude an aircraft can achieve where the maximum rate of climb goes to 0 will be the absolute ceiling. So this point is actually the absolute ceiling, and this is just for the reference which we learned in our previous lecture, that it is a graph between the vertical component of the velocity with which an aircraft is going upward during a climb performance and the horizontal component of velocity with which it is moving forward during climb. And the vertical component of velocity varies with horizontal component like this fashion. Okay, and the maximum rate of climb, or the maximum rate at which the aircraft is moving upward, okay, actually climbing upward, okay, is the vertical component of velocity, which is the maximum point of this curve, topmost point, which is given over here, and it cuts over here. And the maximum climb angle is not the 90 degree, it is climbing at some angle. Okay, it is going at some angle which is theta max. It is not 90 degree at which rate of climb should be maximum. It is not. Intentionally we can intuitively we say we can think that it should be 90 degree, but it is less than 90 degree, which is theta max is the maximum climb angle an aircraft can achieve, okay, for a climb performance. So now let's move on to time to climb. So if an aircraft is moving from a point h1 at time t1 to a point s2 at time t2, then the rate of climb, from the definition of rate of climb, we know it is dh by dt. Okay, so from this, if we take dt over here and rate of climb down, we get dt equals to dh by rate of climb, and the time period can be obtained upon integrating both the sides, here with respect to time, here with respect to height, from h1 to h2. So here we got the time, or the interval t2 minus t1 in which the aircraft can climb from h1 to h2, and typically we see the variation of rate of climb which is in the denominator. So that's why we have rate of climb raised to power minus 1 over here. Also here also we see rate of climb raised to power minus 1. Okay, so rate of climb in the denominator, when multiplied by dh, it is keeping rate of climb in the denominator. So height divided by rate of climb, or say height, it is still divided by rate of climb. When they both are multiplied, keeping rate of climb in the denominator, we get the time interval, or say the time period in which an aircraft can climb from a point to another point. So this means that, like just like the distance is equal to speed into time graph, we have, as I said over here, the vertical component of velocity is the rate of climb. Here the velocity is rate of climb, distance upon speed is time, which we can see over here. And from this we get that the area under this rate of climb inverse curve and height will give us the time period in which an aircraft can climb from H1 to H2. For a propeller curve aircraft, we get the time period to cover the same distance or same height, that is H2 minus H1 equals 6,000 meters. An propeller airplane will cover this 6,000 meter in 27 minutes, whereas the jet airplane will cover this 6,000 meter in 3.5 minutes. Okay, so this is showing that jet airplane is highly efficient for a climb performance. Okay, so we will continue with range and endurance in the next lecture.